Okay, next situation, we have the x-axis, a current I flowing along the x-axis, constant current, flows along the entire x-axis, an infinite line of current. We have a square loop. Square loop has sides A, and it's at proximity B. This side is at proximity B to the current, and this side at proximity C to the current, and of course C equals A plus B. So I didn't really have to specify a C, but I went ahead and did it anyway. Okay, so the question is, what's the resulting magnetic field through the loop? So you're going to want to think for a minute. You're going to want to think about what the magnetic field due to this line charge is and how that's going to affect the flux of the magnetic field through the loop. The first thing you should have realized is that the field, by the right-hand rule, thumb along the field, right hand curling around the wire, the x-axis, the field's going to be coming out of the plane of the blackboard above the x-axis and going into the plane of the blackboard below the x-axis. So I've got field here, and I've got the field getting less dense as you get further from the axis. Now, the field here looks more dense than it does here, but it isn't. But in any case, we have the field here going into the blackboard, so that we're getting a flux through this loop due to the field that surrounds the x-axis. Now the question still is, what's the total flux in this loop? So what do you think your next step might be, assuming you've taken this step? Okay, well, the magnitude of the magnetic field at distance r from the wire is 2k prime I divided by r. So we know the magnitude. If we know the position or the distance from the x-axis, we can figure out the magnitude of the magnetic field passing through this loop. Now, how are we going to get to that? We have a variable magnetic field. It varies from one end of the loop to the other. This suggests we're going to have to integrate something. So how would you go about setting up an integral for the magnetic flux? Well, we're going to have to integrate because the magnetic field changes with r, the distance, and there are points in here that are different distances from the current. So first thing we want to do is we want to find something to partition so that we have a constant magnetic field within each partition. What is it that we can partition? You should pause and think about that, but I'm going on now. What we need to partition is the distance from from here to here. Okay? If we partition this square, and I'm going to redraw the square down here. Okay? If we partition, let's say, this side, then within each partition, r varies only a little bit. Okay, so we partition this side, and then we run strips across the loop parallel to the current, so that r is close to the same, r has close to the same value throughout this strip. Now, if this strip has width delta r, and if we have some radius r star, and let me go ahead and draw this strip in here so we get it. Okay, so here's our strip. We don't have room to label the delta r, but that's the width of the strip. And the key thing we need to get here is r. So if this is some distance that brings us within this strip, some distance from the x-axis that brings us within this strip, then we have a representative value of R from which we can calculate. So if R star is a sample R in the strip, then 2K prime I over R star is the sample magnetic field strength, and we apply that sample magnetic field strength throughout the strip so that the flux in the typical strip is magnetic field times area, which equals, in this case, 2K prime I divided by R star multiplied by the area of the strip. Well, the length of the strip is A, the length of an edge of the square, and the width is delta R. So it's little a delta R. Now, what integral do we get if this is the contribution of an arbitrary strip? What sum do we get to give us the total flux? And how does that sum lead us to an integral, and what is our integral? Okay, well, the flux of the typical strip being this, the sum of the fluxes in all the strips, this just being the typical strip, it's going to be sum of, I'm going to call it sum of phi b. That should be capital Phi, so let's capitalize it. And that's going to be the sum of this expression, where R runs from little b to a plus little b. Now that approaches an integral. What integral does that approach as we let the delta R's approach 0? Well, that approaches, arrow from here up to here, this expression approaches the integral from R equals b to R equals a plus b, integral from here to here, of this expression 2K prime I over R. Your R stars get confined within shorter and shorter intervals, so they become just plain R when we approach an infinite number of intervals. And we get 2K prime I over R dr integrated from here to here. And I'm not sure I wasn't in the way there, but we can see that the R star essentially becomes an R, and we get this integral. So perform the integral, tell me what you get. Okay, this integral is a simple integral accessible to first year calculus. We're ways beyond that, so I'm not going to go through the details, but this is what I get for the integral. Check me, make sure I'm right. But this would be the flux. So that would be the flux of the magnetic field. Now what we're interested in is the EMF induced around this loop. Now, if the loop is stationary, and if the current and therefore the magnetic field remain the same, then there's no change in the flux, so there's no induced EMF and no current induced, assuming this is a conducting loop. However, if we move the loop toward or away from the current source, then we are going to change the magnetic field. Since we know the expression for the flux, we are going to change the magnetic field. We're going to change the flux, more importantly. Magnetic field through space will stay the same, but this is moving a different part of space, so that the flux is going to change. We have the expression for the flux, and we can use that expression to determine the rate of change of the flux, and therefore the induced EMF. Another thing we can do is we can vary this current I. If this current I changes, that's going to change the flux in this loop. And what is that going to be like? What kind of result are we going to get from that? Again, we have the equation for the flux, the integral, the expression for the flux. How are we going to deal with that? Well, we'll deal with it in another video.